what is OME-Zarr? OME-Zarr basically is one of the chunked file formats. So as you see in many traditional file formats, the data is not chunked. So they are plane-wise chunked, let's say, for example, TIFF. This means that the individual planes are monolithic, so they cannot be, you cannot get subset, you cannot access subsets of individual planes. And this means that you have to read individual planes if you want to get three-dimensional data, for example. On the other hand, the chunked formats such as OME-Zarr are arbitrarily chunked along each dimension. So you can receive random subsets of the data. And this is very important when you have big data, because very often you don't need the entire data at a particular time. You just need subsets of that. And you can very easily get different subsets of this data, as you will see also in the upcoming slides. So this is one of the main properties of OME-Zarr. And the difference from other chunked formats is that each chunk in OME-Zarr is saved to a separate file. So each of these cubes will be saved to different files. This is especially useful when you are working with data remotely. So when the data is remotely stored, for instance, in an object store. And that especially like speeds up the parallel writing to remote storage. So in this regard, OME-Zarr are even more advantageous than other chunked formats. And OME-Zarr specification natively supports multiple resolution layers, so-called resolution pyramids. And this is also useful for big data, because when you want to access the entire data, for your visualization tool, for example, can alternate between different resolution layers. So when you want to see the entire image, it would switch to one of the lower resolution layers. And then you want to access more detail, higher resolution, then it would switch to the higher resolution layers. I will also show it a little bit more in detail. So this is, for example, when I was talking about like when you can access random subsets. Let's imagine that you want to just visualize this slice in a big data. If you want to do this with TIFF file, for example, then you need to load all of these planes into the memory, because these planes are not divisible. So you cannot just get the pixels, the lines of pixels corresponding to this plane. You have to load the entire, all of these planes. But if your data is chunked in a more cube-like parts, then you can only load those chunks that correspond to this plane into the memory. So it is much more memory efficient. And you can just generalize this to different shapes, different subset shapes. So you can just collect those chunks that correspond to those shapes. That's very advantageous also, and yeah, you can also very easily load this region of interest from, for example, S3 object storage. And in the same manner, why we need resolution pyramids? If you imagine that this frame is, for example, represents your memory, then if you want to see the entire image, which is normally like in full resolution is bigger than your memory, then your viewer will just load the first resolution layer that actually can fit in your memory. So it will automatically do this. And if you want to see greater resolution, then your viewer will switch, alternate to this higher resolution image, but then will only load these chunks that fit within this frame. So it fit within your memory. In this way, you can really visualize like terabyte scale images as well. So it's a combination of chunking and this multi-resolution layout that really makes OME-Zarr quite advantageous. And you can learn more about OME-Zarr from several publications. So this is the original publication, which also benchmarks the performance of OME-Zarr and compares it to different file formats, including TIFFs and also other chunk formats like HDF5. And then we also have this community paper, and this is more about the tool ecosystem around OME-Zarr. And then we also have very recently this hackathon paper preprint. This took place recently at the end of last year and was also published just very recently. So I would like to now take a closer look at the format. Just also continue with introducing the format, especially for those who are not familiar at all with OME-Zarr. I would like to introduce the training material that we are maintaining. This is just basically for really getting familiar with OME-Zarr. So if you are interested in using the format for anything, then this could be a nice place to get started. And basically, we provide some modules for training modules for different task categories, like how to inspect and validate OME-Zarr. And this is where usually there are examples for both local OME-Zarrs as well as those in the S3 object storage. And then there are modules for like opening OME-Zarr, for instance, modules for Fiji related, so Fiji and Fiji plugins, also for Napari, and also for reading into Python environments, even also for web-based viewers. And you have such modules for like opening, saving, and also there are dedicated conversion tools, and we also have modules for those. So if you want, you can visit this site and learn more about OME-Zarr. And for the moment, I'm only going to use it for just for the introduction part. And so this is basically what the simplest OME-Zarr would look like. So you can just have one chunk. So if the image is really small, then as I said, you don't need to chunk it extensively. Then you can also have a single chunk. Chunk would have the same shape as the image array. And then you also don't need to have multiple resolution layers. Then you would have something like this. So it's a folder structure, and usually it's represented in nested directories. At the top level, you would have the resolution layer, the top resolution layer. And then you would also have multiple chunks corresponding to different axes. And you don't have to basically have nested directories. You can also use dot as the path separator for chunks. Then you would have just one file sitting here. So in the first resolution level, in the first array. And that's also possible, and it's allowed in the specification, but it's not recommended because very often in file systems, the nested directory structure is more performant. Then you have usually, so in the simplest case, we would have like these two metadata files for OME-Zarr. This is where the pixel metadata is stored, like pixel sizes and units and other things. And then here you would have more chunk-related metadata, such as the shape of the chunk and the shape of the array, and also other things like the compression parameters. So this would be the simplest case. And this is how the metadata file for this Zarr attributes file, multi-scales metadata file looks like. You can find this pixel information here, the dimensionalities, and the units for those. And then you can find the pixel size here under the coordinate transformations section. The reason for is that in OME-Zarr, you can also store different types of transformations. And there has been like a very long discussion around this, what kind of transformations we can specify and what we can represent. As far as I know, the translation can definitely be represented. So you can provide a translation vector here, the same way that pixel scale is represented, and then many viewers actually can recognize that. So I'm not honestly up to date with where exactly we are, what exact transformation methods are now really in the specification, But I know that people are actually trying and using for their custom setups. And yeah, that's why like we have the pixel scale represented here, and then if we have multiple resolution layers, then we would have multiple such fields for each part. And this is how a typical simple Zarr array metadata file looks like. So it provides chunk shape and the actual array shape and data type, as well as like parameters like compression parameters and the Zarr format version and other things. And if you have multiple chunks, things of course start getting complicated. And if you have really a big data and very small chunks, then you would easily have, as we discussed, like thousands, even millions of files, millions of chunks. And so here multi-scale metadata doesn't change because basically this is more related to chunk level differences. But you see that now the chunk shape is different. And then if you have multiple resolution layers, then you would have two directories at the top level. This is the resolution level 0, the full resolution image. And then we would have other resolution layers. Then we would also have other Zarr array metadata files. So we always have one single multi-scales metadata file, but we can have multiple Zarr array metadata files. And by the way, this is all for just standard image layout. So this is completely different for high content screening layout. So there are two basic layouts for OME-Zarr version 0.4. So this is then, yeah, you would have two different Zarr array metadata files and different shape, of course, because this image is downsampled by half. And then this is also reflected, as you see in the pixel size. You would have 2 times the pixel size compared to the full resolution image, of course. And basically, that's about that's the simplest scenario for OME-Zarr. And there are, of course, there are factors that makes it a little bit more complex. For instance, you can also store label images, segmentation labels in the same hierarchy, or you can definitely have more metadata fields such as visualization metadata. You can also store visualization metadata in OME-Zarr. So I'm not demonstrating those here. But it's important to know, so you can store your visualization metadata, and many viewers will recognize and directly open your image with those visualization settings. But I can actually, as a time permits, I can provide some examples during the hands-on session. And with this, now I think we can actually proceed to the hands-on section. Then, we also have these in the links, but you can also use those links from here. And you don't have to so you don't have to log into Band now. Actually, it's better that you don't log in. I will basically do the demos only, so we don't do this simultaneously at the moment. That's mainly because the Band resources are apparently not sufficient for big participation. The participation of so many individuals at the moment. Therefore, I decided to actually do it in the form of demos. But after the session is over, then you can simply log in and do the practices also yourself. And I just want to say at this point that we have 2 different Band instances. Actually, we had Band only on this Tübingen instance until yesterday. So yesterday we just heard that we have this SESNet instance in place. And from this point on, we will basically provide Band as a Euro-BioImaging service. So you can also simply contact us if you want to use it, for instance, for training courses, or even for like image analysis service provision. And we would help you. So we would restrict resources for that specific period of time that you are going to use Band for your event. And now that we are somehow with the SESnet instance in place, we can say that yes, we have somehow sufficient resources for such courses, because the Tübingen instance was a little bit limited in that sense. But this came just recently, actually just yesterday, so I'm going to use only the Tübingen instance for today. Then yes, how would you start with band? Actually, so I can directly show it from here. So when you come to band, then this is the page, the initial page, and what you need to do is just you agree to this and then you log in. So when you do the login for the first time, it will request that you authenticate with your Google email. So Gmail, you can use your Gmail to authenticate. And once you are authenticated, you will get to this page. So it will open this page. And there you can actually specify your resources here. So number of CPUs, memory, and for certain cases, if you need, you can also have some GPUs. And then you click launch, and then it will create a desktop. So I don't have to do this because I already have this desktop that I will use. But this is how you create your desktop. And one important thing with band is that it is a persistent file system. So it means that you can log in, so you can create your desktop, you can create files, make changes, and those changes are persistent. You can kill your desktop once you are finished, and it is advised that actually you kill your desktop. But this doesn't mean those changes are gone. So they will still be there. And when you create a new desktop, then you will also find those files, data, and everything there. And in this sense, this like launching and killing a desktop simply means you are releasing the resources. So you are advised to really kill your desktop once you are finished in order to release these resources. So this is quite useful because then you can create, for example, Conda environments. You can keep it there and use it for multiple events, multiple courses, for example. Okay, so now I go to this desktop that I created earlier. So this is the desktop appearance, and then and here is your home directory. And for this specific case, I actually created everything in a more global file system location. So you can come to Scratch and NGFF workshop. So I just prepared some data. You can find those here, and I can actually learn. So you can find these here. There are some data sets, examples data sets that we are going to work on. And also I prepare some comments here just for convenience. Then in band, so we are going to basically use this quite often, but I can just show you what is there on band. Basically, there are a bunch of image analysis tools, and so there is Fiji and Napari that we are going to use today, but there are also many others that you can experiment with. And on band, basically, each of these tools are containers. So if you want to, for example, make your own tool, your own custom tool available on band, because you may want to use it for example, a training event or even for image analysis services, then you can simply contact us. If there is a container, a singularity container, we can already directly make it available on band. Otherwise, we can also have the containerization process. And then, you can make it here available here, and then everybody can use it. It's also good for visibility. So for this, then we also have this terminal, and we will use it for the initial steps of this workshop. So the workflow of this workshop is that we will create some OME-Zarrs. We will convert some of these data from different formats into the OME-Zarr format, and then we will open those OME-Zarrs in different tools like Fiji and Napari. So this is the main workflow. And for that, I created earlier a Conda environment, and on Band, in order to work with Conda environments, you need to first source those Conda using this script. So that's just a measure, because if you already try to make it automatically available when you install Miniforge, apparently there's a step which can be a little bit dangerous for Band, so we don't make it available automatically. We just source it every time. But yeah, we will work on this and hopefully eliminate this issue. Then we can activate this environment with the name of the environment is NGFF workshop. And then we go to this directory, where the data sets are. Now we are there, and so the tool for the conversion, for this particular workshop, I'm using the tool that we are developing here at Euro-BioImaging, which is called UB-Bridge. But I just want to mention also the other tools. There are quite a few tools that you can use for conversion. Actually, I can show you some of these here. And basically, there are many different tools, and this list that's here is definitely not complete. And different tools can be useful for different things. You can indeed create an OME-Zarr from Fiji. You can just open your image in Fiji and then write it as OME-Zarr. But that might not always be the best strategy, because if your image is big, then you cannot open it on Fiji so directly. And therefore, there are these dedicated converters that are a bit more smart about this process. So they create the OME-Zarr without filling the memory. So perhaps the most frequently used one is Bioformats.ro. It is coming from the OME community, and maybe you can think of this as a standard way to create OME-Zarr. It also can read images from different formats, as it uses bioformats in the backend. And there are also some other tools that are built around Bioformats.ro. These include the NGFF converter, which is a graphical user interface. So Bioformats.ro itself is a command line tool. So NGFF converter is built around it, and it is more easier to use, as it gives you this graphical user interface where you can create conversion jobs. So you can also parallelize the conversion process. And batch convert in that regard is quite similar, and it also parallelizes the conversion process over multiple files. And it also uses Bioformats.ro in the backend. It also can perform conversion, for instance, on Slurm clusters, or also combines the conversion to data transfer, so you can convert and directly write to an S3 bucket. And lastly, we have UB-Bridge. It is the main motivation also behind having this additional tool is that sometimes you have situations where your big data is stored in multiple files. So you have images that are basically different time points or different channels, but they belong to the same image series at the end. So you can convert and group them at the same time. So you can combine the conversion to concatenation along specified dimensions based on the patterns in file names. So I will use this tool and also exemplify this kind of conversion here. So coming back, then, so first of all, we have some images here. So in this folder, we have multiple images from different formats like LIF file, TIFF, and LSM, and also CZI formats. Then if you want to perform this unary or one-to-one conversion, where each input file is converted into one OME-Zarr container, then you can run a command like this. So basically, this is the command. So easily, it is ub to Zarr, and then the input directory with multiple files, and the output directory, which I simply named results in the same folder. And then this is completely optional if you want to perform this conversion on Slurm. So if you want to use cluster resources, you can specify this as true, and it will automatically submit Slurm jobs. But you don't have to do this for small data sets. This is only for demonstrating. You can very easily use your own user node for this. And then it performs the conversion. And by default, it also creates 3 resolution layers. So two additional resolution layers. So you can actually see the result. So now you see that each image became one, it's like converted into one OME-Zarr. And it also creates this OME-XML, which is also, actually, it's not obligatory to have this in OME-Zarr, but it can be useful. So it is temporary, I would say. It won't be around in the next OME-Zarr versions. But for the moment, it can be quite useful to have it, because you can also have your acquisition metadata and other things for which we don't have currently any OME-Zarr specification. So we have quite extensive metadata specification from this traditional OME-XML. So that was, as I said, that was a one-to-one conversion. But UV-Bridge also can perform what I named as aggregative conversion, where you want to combine multiple files into one file, or one OME-Zarr container, sorry. And in order to do this, you just need to additionally specify these tags. So let's first have a look at the input image that we want to convert. So that one would be here. This one, I think. This is so you see here that the images, the TIFF files that basically represent different channels and different time points of the same image. And you want to create one OME-Zarr out of this. And for that, you need to make sure that the tool knows which pattern corresponds to the time dimension and which pattern corresponds to channel, because these are the dimensions that you want to concatenate along. And what you do is you provide, so first of all, you have to check if you have such a pattern, like a specific string followed by a number that represents the index. So if you have such kind of file naming, then you can actually simply use this pattern as a tag, and the tool will simply look for any such pattern followed by number, and then it will use this to represent that particular index. And then you also do this for time point. So therefore, we specify time tag as t, which is followed by a number, and then channel tag for channel, and it's also followed by a number. Then you also specify along which of these axes you want to concatenate. We want to concatenate along both axes in this case. So we specify like T and C here, and then that's it. That's basically everything. So we can actually run this command. Then we get this output. Now it also created the, maybe I also see the metadata files. So this is the output folder, and you see that it's simply just reduced this file multiple numbers to this string as set. So it's a channel set and then it's a time set. And we have 3 resolution layers, again, created by default, but you can also update these. You can basically specify how many resolution layers you want to have. Also, other parameters like what the chunk sizes you want to use. By default, it uses a 256 pixels as the chunk size along Z, Y, X. And yeah, it also performs an isotropic downscaling. So it uses a scale factor of 2 for along Z, Y, and X.
Sorry to disrupt, Bugra, but it seems there's a question in the chat from Alex about the channels. Do you want to address that maybe?
Yes. Let me see the... For an RGB image. So yes, you can have, so in that case, actually, you can have 3 channels, but this should be available in the input format. So it should be specified like that in the input format. Then yes, you would actually have definitely 3 channels, and it would be converted in such a way that in the OME output OME-Zarr, you would have 3 channels for that. And any other questions so far, actually? You can just also put it in the chat. And then I will also show one more example, and in this case, it can be, so life cannot be always so easy. So sometimes we have different file naming patterns. Actually, very often we have quite different file naming patterns, and we don't have this ideal scenario where you have like in this image. Let me come to that example again. So we don't have this ideal scenario where you have this channel and time tags are just followed by simple numbers, and then you can use these strings as patterns. But rather we have more like categorical labels, something like this, for example, or something like this one here. So we just have categorical labels, especially for channels. Often we just have something like this, or like GFP or blue, red, whatever. And then we should represent these differently at the command line. And by the way, I also want to say this specific point, you can also have nested directories. The tool treats these nested directories the same way as the flat list of files. So this is basically completely the same as this one. So you can convert both of those in the same way, mostly with the same command line instruction. And yes, and now in this example, I would like to convert this image, this folder. And the way that you specify such categorical labels is like this. You can use a comma separated list. So these are the patterns that represent different channels. So you provide these different patterns representing different channels in the form of a comma separated list. And for time, in this case, we can use exactly the same approach as in the previous example. We can specify just t because we have this pattern t, this regular expression t followed by a number. And then this is what I do. I simply copy paste this one. And this image is a little bit bigger, so it's, I think, somewhere between 15 and 20 gigabytes. So it would take probably a little bit longer. So it created this folder. And it put this H2BMG 2 times because it appears in 2 different places in the file, in the files. And then this is basically a time course image. It has like 270 time points. So actually, since the default order is always like time channel Z, Y, X, then we can actually expect these different time points accumulating here. So you see that we have at the moment 112 items, so it is accumulating there. Make it it creates first the highest resolution layer, and then it applies downscaling to that. And you can also specify parameters such as scale factors. It is by default 2, and very often in most OME-Zarrs actually you would see a downsampling factor is 2, but you can also change this depending on your use case. So the first conversion is finished, and now it is doing downscaling. And now it is converted. So this is then the output. Maybe I just, yeah. So this is basically the output. Then what we can do now, so basically this is how you can do the conversion. And in this way, yeah, you can create different kinds of conversions. So just to sum up, you can perform unary or aggregative conversion. So you can either convert each input to one output, or you can concatenate them. You can couple the conversion to the concatenation. Now we can actually continue with how we can examine these images. So I would like to first start with the Fiji. So Fiji is one of the most frequently used tools. So how we can open an image, an OME-Zarr image in Fiji. So you can go to these applications and then image analysis, and then choose Fiji here. Okay, yeah, it cannot be updated. It is read only because yeah, in band we do the updates actually. At least for the applications that are here. So you can also always install your own applications, for example, in a Conda environment, and then you can treat them as you like. So they are basically your own tools. So how we can read an OME-Zarr into Fiji? So this is very simple actually. Now the recent versions of Fiji come with this option. So you go to import, and then you go to this HDF5 N5 Zarr OME NGFF reader. So as its name suggests, it can read all of these different chunked formats. Then the easiest way to open actually is to paste a path here. And the good thing is it can also detect data sets that it can open. So for example, we can just paste this whole path containing all of these OME-Zarrs. And then we click detect datasets, and then it will detect all the datasets, all these are arrays that it can open. So it's just provided full list of the OME-Zarrs that we created. For example, let's say we want to open this one, this nuclei.zarr. It already gives us some information, like it tells us the shape of the image. And you can also get the size of the image. You can have an idea if this is too big, or if it fits the memory that I have or something. And in this case, definitely I can also open the top layer, top resolution layer. So I click this one, and then I click OK, and then it opens. So it is a 2-channel image, and we can easily see both channels. So what happens, for example, if I have very large image, or if I have just an image that is bigger than the memory I have, I can also try this. Let's paste the same. So for instance, this last conversion that we did, it was a little bit bigger. Indeed, when I created this desktop, I specified that my RAM is 8 gigabytes. So this image, I know that, so I can see that this is 16 gigabytes. So it is larger than the memory that I have on this desktop. So in this case, I definitely would not load this into the memory. So I would specify a smaller image like this one. And this is much easier to manipulate on PG. So I click that one and then click OK. And then this is basically what I have. Can I just make it a bit bigger? So yes. So this opened, of course, with a bad brightness contrast adjustment. So I can correct this one here. So this is basically how it works. And now this is just a PG image. So when you have an image like this, it's basically just a standard PG image. You can do anything you want. You can process it the way you like. And it's also a 2-channel image. And for instance, for what you can do, you can convert it into a channel image. You can into a color image. You can come here and then this channel tool. Yes, so it is then like this. Can also do the brightness adjustments. So then it would look something like this. So you can also do other types of processing, of course. It's just the Fiji image. An important point here is, does it also see the metadata correctly? Because as you see, when I read into Fiji, I simply choose an array. I do not really open the multi-scales. Let's see it again, maybe it's easier. So it gives me these results, and then I do not open the entire image. I specify a single Zarr array inside this multi-scales or pyramidal layout. I can, for example, open also this image and also compare the metadata to the metadata of the original OME-Zarr folder. So I just click this one and then OK. And I come here and see the metadata. So it tells me the voxel size. So this is a conversion from LSM, and this is the pixel size that were saved during the conversion process, and then it was read into Fiji. So when we read the OME-Zarr, it could detect this pixel size, and then what we can do is we can go back and check the same conversion. So is this the correct one? Actually, this is actually wrong. So I need to get into this. No, and I was looking at the wrong resolution layer apparently. So it is correct. So the top layer resolution that actually shows that the pixel size is 2.024, and it's also confirmed in Fiji. So this is just a quick check to confirm that Fiji can recognize the metadata correctly from the OME-Zarr. And also, yeah, it's you can also see other kinds of information. So I have to say that not all OME-Zarr viewers can currently read all metadata. So this is always when you are working with OME-Zarr, it is because of the fast evolution of the tooling ecosystem, and also the metadata is evolving quite fast, and sometimes you just you count on like reading metadata correctly, but you see that it is not the case. This is especially true with visualization metadata, but even sometimes with pixel metadata. For instance, some tools require certain naming of the units or certain representation of the pixel sizes. So it would be quite important to always double check when you are using any tool. And now I would like to show one more thing at this section. And when you open with this M5 viewer, M5 ImageJ tool, this is the name of this reader, M5 ImageJ. There is also this option to specify crop. So as I said at the very beginning, in OME-Zarr, you have this freedom to really get subsets of the image. So you don't have to load the entire image into your memory. So this is one thing you can do also here. Let's say we come back to this one and we really want to see the top resolution, something from the top resolution image. What we can do, we can just specify a time range. In that case, in order to do this, you simply come and click this crop and then click OK. Then it gives you this window where you can specify a subset, a region of interest. Here, you just need to be careful about the pixel or the dimensionality ordering, because in most Python tools, we have this, the default order of axis is time channel Z by X. But in ImageJ environment, it is usually different. So in this case, you see it is X, Y, Z, channel, and time. So this is actually the time. Let's say I just want to open the first 10 time frames. I can do this, and I can also, if you want, you can also specify other axes. Then I click OK. And then you see this is then the full resolution image, but only the first 10 time frames. Yeah, so this is basically some of the things that you can do with when you are reading OME-Zarrs into Fiji. And now maybe we can move on to the next tool. Sorry, I just need to do something. Also briefly check the chat. Yeah. So the next tool that I would like to demonstrate is the Big Data Viewer integration with OME-Zarr. So you have basically the same name, this HDF5 M5-Zarr OME NGFF viewer. And the aim here is to really open the entire multi-scales. So in the M5 image, as you noticed, we always read images from arrays. So because in Fiji, you cannot represent a multi-scales object. You just can represent a single array. But in the Big Data Viewer, you can represent also multi-scale images. For instance, so it gives you exactly the same window, by the way. This is also a good convenience. And if I want to go back and just maybe get the full results section again and detect datasets. And here you might already notice a difference. So this time the multi-scales are also selectable. So these fields were not selectable in the M5 ImageJ because you had to really specify which resolution layer you want to load, because it as I said, it only can load arrays, and it loads the arrays fully into memory. So it doesn't do lazy loading. On the other hand, here you can the lazy loading is also supported. You simply specify this multi-scale hierarchy, and it will the reader, the viewer will decide on which of these fields to show depending on your zoom factor, so how much you are zooming in. So I simply select this and then click OK. and it opens in N5 viewer. And what it is, there's something. This is a bit strange. It didn't really. Okay, it was just very bad brightness contrast adjustment. So I can specify the color as well here. So for example, I specify magenta for this one. And then you can also specify color for the other channel. First, we just bring this into the view. Then it looks like this. And you can browse through time. Basically, this is just typical big data viewer. So you can do anything that you do with other image types in big data viewer, you can also do here. So you can just rotate. You can browse by using mouse browsing. So you can do just anything that you do with big data viewer. And this one also recognizes the metadata correctly. And yeah, just notice that this is a hidden button here. So if you want to do anything with brightness contrast or any kind of visualization settings, you just come here and then you find this here. And you have the same or similar settings also here. There is this brightness color. You can also do this. This is just legacy, as I heard that this will disappear in the next versions of Big Data Weaver, but it is still there. And yeah, so this is basically how it works. I would like to also show one quite interesting feature of Big Data Weaver. Sorry, yeah, I think that this image also has probably a wrong. Original image is probably wrong in the axis ratio. So the if we see the metadata, actually this is, I think, the original TIFF files that we converted from apparently didn't have correct pixel scaling, so it just had the number 1, which is default. So it was also converted like this. So that's why you see that the aspect ratio when you rotate seems a little bit odd. And one thing I would like to show, which I like in OME-Zarr, is that you can easily update this metadata. We can even do this manually, which is normally definitely not the good practice. You should do this automatically from the command line. But just for demonstration purposes, we can change the aspect ratio. For example, let's say the correct ratio should be like 3:1, and then we can change this to 3, and we can also change this with the same factor 3 times. So it would be like 6 for the second, and for the third layer it would be like 12. Let's do it like this, and then let's save this, and then we just read this into Big Data Weaver again. This one. This is quite tricky. Okay, but we can already have a look. Now, when we rotate, you see that actually you don't see the huge difference between along the z-axis and along xy axis. So this is a good feature of OME-Zarr. So you can very easily update metadata. If you know that it is wrong for any reason, you can also do this with visualization metadata. At the moment, I have not yet integrated visualization metadata with this UB bridge tool, so you don't see it here. But there is also another field called OMERO field, in addition to this multi-scales field. In this OMERO field, you can also specify brightness, default brightness contrast adjustments that would be recognized by viewers afterwards when you try to load the image. And now I would like to show another option, which is just reading a big image from an S3 object store into Big Data Viewer. And for this, we can go back to this file where I actually have the URL to this big data set. So this is a data set that is hosted on the Amble S3 bucket. It is roughly 8 terabyte in size. And the good thing is that if the image is sitting on a public S3 bucket, you can very easily open it in many readers, many NGFF readers. And in this case, we can try this with the Big Data Viewer again. And what you do is here, instead of putting a local path, you just put this path to to the actual image, actual multi-scales hierarchy on the S3 bucket, and then detect data sets. And you see that it gives you many different resolution layers, and also it gives you these labels. The good thing is that you can store label images, so segmentation images, in the same hierarchy. So there is also a specification for this. And when you want to open an image, you can choose either of these. So you can choose this one, or you can choose the label images, or you can choose both of them. So you can also specify both of these. And then when you click OK, then it gets the image from the S3 buckets, and you can visualize, and you can do everything that you do with local images. And you see that now you also have cells represented a little bit like channels. Actually, it's not channels, but it is seen a little bit like that in this visualization settings here. And basically, yeah, this is basically the label image. You can also choose which one you want to see. And this is how you open a remotely located image. And finally, before concluding this Fiji session, I also would like to show you one interesting feature that we have, that this N5 viewer basically offers. Let's say you want to really specify a region of interest here, and then you want to process that. That's actually a little bit similar to what we did with this crop option in the earlier tool, like when we wanted to really load the OME-Zarr into Fiji, we had this crop option where we specified the time range. And this is similar, but in this case, this is a little bit more fancy. It basically gives you a window, a cropping window that you can interactively play with. So to achieve this, you go to Tools and to this Extract to Image J button. And when you click, you get this nice bounding box, and it's also you can also see it here, and you can move it. Specify which part of the image you want to actually extract to image J. And one interesting thing with this is that it also tells you what is the size of the data set inside that cropping window. So you see that you can also choose which of the resolution layer you want to crop. It makes sense when you have like terabyte scale image like this. Makes sense to choose, for example, one of the lower resolution layers. And then it tells you the size of the output. So in terms of pixel size and also in terms of the actual data size. And now we are okay with this value. This would not be too much for our memory at the moment. So we can live with this. And when I click OK, it will just extract this region as a Fiji image. Like this. This is also quite useful, and imagine that like you have a huge image sitting somewhere on an S3 bucket, you get a subset of it and you process it. So that's basically quite convenient. And yeah, with this, I would like to conclude the session for PG. And next, maybe we can also have a look at how we can open an image in Napari, an OME-Zarr image in Napari. This is actually pretty simple, and you also have an Napari here, by the way, but for this case, I think I found it's a bit faster when you use the Napari from this Conda environment. Maybe it's a version issue. So I will use the Napari from our own Conda environment. You can simply type Napari. So it's important maybe to say that PG still doesn't support drag and drop for OME-Zarr, so you cannot drag and drop onto PG and it can actually crash. But Napari does. You can just choose an image. Maybe we use the image that we created last, this relatively bigger image. You can drag and drop it on Napari. And important to know that Napari by default doesn't open. You just need this Napari OME-Zarr plugin installed. And the easiest way to get this actually directly Conda install Napari OME-Zarr. And it opens like this. Then we can also maybe specify the brightness contrast a little bit. And I would say it's also quite performant with this data set size. So this is also how it works. So I would say that's it for the viewers that I can mention. And maybe I also now move on to the next session where we cover how we validate OME-Zarr and how we can inspect metadata without really opening the actual image on a visualization tool. So there, I would say that the most comprehensive tool to inspect the OME-Zarr metadata at the moment is this so-called NGFF validator. And there are different ways to access it. This is actually a browser-based tool. And you can simply construct a link on your browser. It would go to that OME-Zarr and it would validate it. I can show you that, but for local images, when you have local OME-Zarrs like you have here, you can also use what's called the OME-Zarr Py library. It's a Python library. It also gives some command line utilities. And this in these command line utilities, it also integrates this NGFF validator. So it works like this. You simply type OME-Zarr and then view. This is the right command. And then provide the path to the OME-Zarr that you want to validate. So you can simply choose this one again. So it opens this browser window, and then it tells us that this OME-Zarr is valid when you see this sign. And it also gives you comprehensive metadata. So all of these things that we discussed, like the axis, or this metadata that you find in the multiscales metadata, in this Zarr attributes file, they are shown nicely here. And it also provides this array metadata, tells us the size of our image. So this is 16 gigabyte image, and it also gives us the size for the individual chunks and also the shape. So I said that the chunk size is by default like 256. It is, of course, not possible for Z because the array is already smaller than that. And you can even visualize an individual chunk. So if you click this one, then you can also specify the indices of that chunk. And you can even just, it gives you this visualization. You can go through this. And you can do this also for all resolution layers that's there. So 0, 1, and 2. This is also pretty useful tool. And also you can use this directly from the browser. When the data is located somewhere on S3 object store, you can also use this from the browser. And in that case, like what you need to do is instead of using localhost, you should provide the path to the remote data. So for example, we can do this with the big data that we have already just for demonstration purposes. We can copy this and we can paste it here. And you see now it validated this remote data. And interestingly, if you have also label images, it also provides this link. And if you click there, then you can also validate just the label folder. So specifically the label images that you have. So this is how you validate your OME-Zarr data locally and remotely. And I think that's roughly everything that I prepared. And I hope that, yeah, this is useful for you. You learned something, and I would be happy if I could convince some of you that it's worth giving it a try. And maybe, yeah, let's see how many of you will continue to log into Band and do some hands-on practices.